Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully you guys are doing so well. I think I'm in one of those big migraine spells myself. Like going to bed did not help. I still have one. It's not as bad as yesterday, but I guess let's keep going. Maybe it's because I'm upset about all these 2% fees we're giving those money managers, right? So upset, they're stealing my gains. All right, let's actually get back into it. And there we go. Again, highly appreciated if you turn your cameras on and participate. I'm actually not going to ask you to participate that much today, but at a couple points I will. And yeah. So we're definitely starting the last section in chapter 3 today. And then we're going to move on to, it'll spill a little bit into Friday's lecture, but we should finish chapter 3 by that lecture. So I'd probably recommend that you do all your chapter 3 homework at some point this weekend. Next week, we will be doing linear programming. And remember, I'm going to show you how to do things in Excel and Python. So make sure that your Excel and Python game is up and ready to go, because that's going to be relevant starting next week. In the meantime, though, let's talk more about interest and payments and making money. Okay, so quick recap of last time. Started out with a story time. The whole point of story time was to motivate doing this. And the whole point of doing that was to motivate deriving this formula, right? So this formula is the more important formula. This is the thing that you need to remember from all that. So you need to remember the future value of annuities formula and when to use it, which I'll talk about. So by the end of chapter 3, we're going to have a bunch of formulas for finance. And because it's easy to get confused with this thing, I'll summarize. Here are all the formulas. Here's when you use which one. But in the meantime, you should be making notes to yourself when to use which formula. So we derive the future value formula. And of course, you can solve for the PMT to get the sinking fund formula. And remember what the future value formula is about. You have some future value in mind, and you know you can get a certain interest rate. The idea is, what should my payments be on a regular basis in order to achieve that future value, right? When you figure out those payments using the second formula that you see boxed here, it's called a sinking fund formula, because an account where you do that is called a sinking fund. I mentioned that, but I actually didn't write that down. I should probably start by writing that down for today's lecture, what the definition of a sinking fund is. So that's that was a formula that we did last time. And we did a few examples, right? So you deposit $1,000 a month. How much do you get after a certain period of time? We can use that formula. We also looked at how just decreasing your interest rate by 2% over a long period of time can really rob you of a lot of money, and the importance of doing that. I left you guys with this example. Hopefully you actually tried it. That's the example we're going to start off with, but that's where we are right now. Let's move to that. But as mentioned, I probably should tell you, for the sake of being thorough, what sinking funds are, etc. So picking up from last time, let's jump into it. Sinking fund. Start with that definition. A sinking fund is an account into which payments are made to achieve some future obligation. Okay, so that's what a sinking fund is, right? It's an account for the purpose of saving up towards something. And we usually use this in contexts where you kind of know what you're saving up to. So maybe an example would be a college fund can be thought of as a sinking fund, or depending on how specific you want to get, maybe a retirement account can work here as well. But that one would be with an asterisk, I would say. It's not always thought of as a sinking fund. Strictly speaking, the thing that makes a sinking fund is, i.e., there is a specific future value that you have in mind. And you want to know what payments needs to be, what your regular payments, what PMT is needed to achieve that value. Certain is a very strange word to use here under some interest conditions. Like someone was asking me in the last class, your interest rate isn't exactly something that you would call certain, because they can change over time based on how the economy is doing, how inflation is going, what the Fed does. Your interest rates can change. So the idea would be, probably if you're doing these calculations for some point far into the future, would be to use like historical data. So you kind of use like the average interest rate within the context that you're thinking about over the past 30 years, 40 years, 50 years, as opposed to whatever interest rate is quoted to you directly in the moment by one particular firm. But that's besides the point. We're dealing with very idealized cases in this class, and they can still help us plan for a lot. So the example we ended up with is, okay.
Professor, can you just scroll back up to the definition for a sec?
Sure.
All
Yeah.
right.
So you good? Okay. Yeah. So that's what a sinking fund is. Just an account. You're making payments into it. And the point is, there is some value you have in mind in the future that you want to save up to. You pretty much want to be able to predict, what payments do I need generally to actually achieve that? For example, here, 18 years from now, you want to have $150,000, right? Let's say, this is some sort of college fund. 18 years from now, assuming that prices stay fixed, which they probably won't, they'll probably go up. You want to be able to send your kid to Colombia for 2 years. Okay. So that might be a goal you have in mind. Just had a little baby, strapping baby boy or girl. You're like, okay, in 18 years, you're going to Colombia, young man. And you're like, that means I'm going to need like $75,000 a year. So I'll pay for 2 years of Colombia. That's the deal, right? You work and pay for the other two, right? So you're like, I know I need $150,000 18 years from now. Now, let's say someone tells me that they can give me 5% APR compounded monthly over that time. Like I said, not realistic that you can bank on that. So I probably even do my calculations on half that interest rate, because you never know. It's 3 years from that point. The same people can come to you and say, "Oh yeah, remember we promised you 5%? The way things are going in the economy, I think we're actually going to have to kind of like drop that down to 2.5% or something." Okay, so yeah, but let's assume we're getting 5% APR over this entire 18-year period, compounded monthly. What payments do I need to achieve that, right? So I don't have $150,000 now. What can I pay per month into an account giving me 5%, that can get me $150,000 18 months from now, 18 years from now. Okay, so this is actually a formula that we used before. So let's just jump into it. Recall, we know that the future value is equal to payments times 1 plus r over n to the nt minus 1 over r over n. Right, so that's the future value of an annuity. And the thing is, we can actually solve for PMT. So this is going to be FV times R over N over 1 plus R over N, PMT minus 1. Okay. So this was the what's called the sinking fund formula. And here, I know what the future value is. In the future, I want 150,000. I am assuming that I will get a 5% interest rate compounded monthly over the next 18 years. Okay. Which means, using the formula above, my payment needs to be, well, 150,000 at 5% compounded monthly. So again, I'm assuming I can get 5% compounded monthly. 12 times per year for the next 18 years. And that is what my payment needs to be. So how much would it cost to have a 2-year Columbia baby? Assuming that the only thing you're worried about is that, right? Or so you want to do that. What's it going to cost? So again, like to have you guys plug that into your calculators. Make sure you know how to calculate it. Please try and someone tell me the answer. I'll wait. Did we get it yet?
Would be 429.55.
That is what I got. So yeah, let's go with that. Hopefully everyone tried it and got that. Again, participation is important. You want to know that you know how to use your calculator before test day. So yeah, I'm in agreement. Who was that? Was that Tommy?
Steve.
Steven. Okay. I didn't look at the name that popped up. Okay. So Steven and I agree. So I'm a go with that answer. And hopefully the rest of you tried it and got that answer. But yeah, so it will cost you around $430 a month to get that goal in 18 years. And because it's compound interest, it means if you wanted the full 4 years of tuition, it would actually cost you less than double that. So you can, if you can afford double that, you're in good hands, right? So, you know, if you're able to save $1,000 a month for the next 18 years, you can send them to Colombia for the whole 4 years. That's how you're gonna make the plan. Yeah, let's continue. So that was the last example in 3.3. We're now going to start the last section in chapter 3. Ultimately, we're going to do 2 examples, and then I will leave you guys with 2 examples to do for next time. So let's actually do that. 3.4. We're going to talk now about present value of annuities. We spoke about future value of annuities. Remember, an annuity is a sequence of payments. Whenever we say annuity, we're talking about ordinary annuities, which means they're fixed payments where the interest is given at the end of each pay period. Fixed value, present value of annuities. And this is also leading to a formula called the amortization formula. So we're also going to talk about amortization. The connection here is very similar to the connection we had last time, where the title was, where did I put the title? Yeah, the title was Future Value of Annuities and Sinking Fund, but they're really, while it says 2 things, they're really one thing. It's just you take the same formula and you solve for the other guy. It's the same idea here. The present value of annuities formula, if you solve for the other guy, you're going to get what's called the amortization formula. And I'll talk about why it's called that and what it is. So just to explain the idea to you, it's almost as if we want almost the opposite of what we had before. So what we've been talking about yesterday and recently is, okay, I have some future value in mind. What payments do I need to make in order to achieve that future value? However, there's another question that we could ask. What if I want to know what value do I need in an account now in the present value, so that I can get payments from that account, right? So instead of me making payments to save up to some future value, I want to know what is the present value I need in order to receive payments until some point in the future, right? This is called the present value of annuities. So I don't want to know what my payments need to be to save up to some lump sum. I instead want to know what is the lump sum needed right now in order to get payments paid out to me. And it's worth mentioning that a lot of times we won't have that lump sum right away. So what is probably more realistic for most people is that they would use a sinking fund situation in order to save up to that lump sum. And then they know once they have that lump sum, they'll be able to get a certain number of payments. So normally when you go to like a retirement planner or someone who's selling you some sort of insurance or an annuity, this formula is going to be important in that situation, as well as when you're paying off debts. I'll talk about some situations where this is important. And when I summarize the formulas and when to use them, I'll also mention the situations you want to use which in real life and in this class. Okay, so let's actually do that. Before that, to prepare for the above, let's go back. Way back. Back to the old compound interest formula. Call A equals 1 plus R over N to the NT. We know that was the compound interest formula. We can write this as the future value is the present value that I can put in at one time, set it and forget it, and achieve that future value. So here's the thing. We could actually solve for the present value here. So that's going to be the FV divided by the 1 plus Rn to the NT. which we know by laws of exponents, which we covered the first week. I can actually write this as FV times 1 plus R over N to the minus NT. So that gives me the present value formula, which is this guy. Present value formula. I do want to distinguish that this is the one-time payment or the lump sum present value formula. The one-time lump sum present value formula, right? So I know there's an environment where I can get compounded interest, and I want to know what lump sum do I have to put in now to achieve some future value if I just set it and forget it, just leave it there. So I'm going to start out by doing just a very simple example. The point of this is not to be realistic or anything. It's just to show you how we can use this formula. And I typed up the example somewhere. Okay, here. So this is the example we're going to do, okay? And again, it's not very realistic, and we're not actually going to save that much money. I'm going to ask you guys how much we're going to save, but there's the example. So I'll give you guys a couple seconds, maybe take a screenshot or write it down very, very quickly. Yeah, so here's the idea. I want $1,000 1 year from now, okay? 1 year, right? So we're not 18 years down the road or anything like that. Let's say 1 year. Let's say I have an account that's going to give me 5% interest compounded monthly. What lump sum do I need to deposit now in order for it to grow to $1,000 in 1 year? Now, of course, remember, compound interest does take a little while to grow. So it's still going to be close to $1,000 that I have to put in order for it to grow to $1,000 in just one measly year. But it's worth going through the exercise of seeing how you'd calculate that. You'll really start to see the benefits farther out than 1 year from now. But let's see 1 year from now. Okay, so yeah, here. I know that I want the future value to be 1,000. And I know that I'm getting 5% APR. It's compounded monthly over 1 year. This means what lump sum should I deposit now, as in the present value? Well, that's just going to be the future value times 1 plus R over N to the minus NT. So that's going to be 1,000. 1 plus 0.05 over 12 to the minus 12 times 1. And I'll actually do this for you guys since it's an old formula. We've been over this, but definitely I want you guys to check on this that you got the same answer. I got 951.33. Right? So how much did I save? Well, the total is 1,000. I deposited 951.33. So I saved the difference, right? So 1,000 minus 951.33. I didn't actually do that calculation. Where's the subtraction? Let's do it. 1,000 minus 951.33. So 48.67. So I saved around $50 by doing this. All right. not a big deal. Um, uh, for saving $50, I would probably just not put the lump sum. I'll probably just do monthly payments, right? It'll be a lot easier, right? So figuring out how to get $950 lump sum in order to make $1,000 in a year, and the only benefit is $50, probably not something I would do, but I would know that, hey, this probably shouldn't be something I would do, right? So because it's only going to save me $50 over the course of a year, probably not worth it. I'll just do some monthly payments. But actually, we don't know the formula for no, we do know the form for monthly payments. So we can do that. But that's how you would calculate this, right? But again, it's 1 year. We don't expect it to be anything drastic, okay? So as we saw last time and over the past couple of classes, compound interest really does its magic over the long term. It's not something you're going to notice from one day to the next. So yeah, but that's a simple example of just using this. Okay, but that is not a very interesting question either, I would say. I mean, that question isn't going to get you excited. It's not going to get you out of bed in the morning, right? Here's a more interesting question to ask, which is what the point of section 3.4 is really getting at. So here is a much nicer question. You know what? Forget about $1,000 one time. What money do I need now so that I can get $1,000 payouts every month for the next 5 years? Now we're talking, right? So how much money would I need in that account, gaining 5% compounded monthly, so that I'm not just going to have $1,000, but I can withdraw $1,000 every month for the next 5 years, right? So this is a question that should be of interest to you. It's the kind of question that you would have to ask yourself if, like in a retirement planning situation, for example. So let's say you expect to retire at 60, and for whatever reason, you expect to die around 90, because my pappy died around 90, his grandpappy died around 90, etc. Right? So like your life expectancy in your family based on your family tree, you're like about 30 years after retirement. So let's say you know that, right? When I retire, I'm going to be alive for about 30 years. Let's say I want $1,000 a month for 30 years of life, right? How much would I need to have saved up by that point, right? So what you can do is figure out what that value is, and then I need at least that by retirement. So what you can then do, set up a sinking fund where you make payments over your entire working life so that with interest, it grows to that number. And then all right, now I can rest easy. I don't have to work. I can just live off this $1,000 a month, because obviously I'm not in New York City, right? Can't live off $1,000 a month. Who am I kidding? This is just for example, nice round numbers, right? So what is that amount that I would need in order to be able to do this? Now, it turns out I won't need the exact amount of money because it's growing with interest. So I actually need less than I would think I would need in order to make this happen. So let's see. If we're talking about a 5-year term, which again, not a super long time in terms of compound interest, like how much money would I need now, right? That's a much more interesting question. And for that, we don't really have a formula for it at this point. We need a formula for this. Right? So this is what we're going to do. We're going to develop the formula. I'll generally talk about the idea very vaguely. This is not a math class or anything. So I already went through the longer derivation of, the sum of a geometric sequence and how we got the sinking fund formula. You can get this formula in a very similar way, but I'm not going to go through the full argument. But the idea is, okay, there is a timeline. Here is now. And I want payments for M periods in the future, right? So if I'm looking for every month for the next 5 years, your M would be 60 in this case, right? There's 60 points at which you want to be able to withdraw $1,000, right? And so I want to know. So let's say the amount I want to withdraw, it's always the same amount. It's R. This is what I want to withdraw. Right, so that's R. So now what I'm going to do is figure out, I need a little more space here, is figure out what is the present value of that, right? So what is the present value? Let me move this over a little bit. What is the present value of that, right? So how we can think of this is to say, okay, what would I have to do now to get this payment 1 month from now, right? Well, that's a lump sum situation, right? That's this formula, okay? So in 1 month, right, like it's going to be compounded once by interest. So my N is 1, my T is 1, right? So I can actually use that formula, right? It's the future value that I want, 1 plus R over N to the minus 1. Similarly, in order to get R dollars 2 periods from now, well, it's that to the minus 2. In order to get R dollars 3 periods from now, well, it's that to the minus 3, and so on. In order to get R dollars M minus 1 periods from now, well, it's that to the minus M minus 1. And in order to get R dollars M periods from now, well, that's N. Well, that's minus M. I want you to notice that over here, this is a larger amount of money, and this is a smaller amount of money, right? It actually decreases over time because you have a negative power and the magnitude of the negative is getting larger. We know about laws of exponents, so we actually know that's smaller. And that makes sense, right? To get a lump sum that is a large value in the very short term, I need to initially invest a bigger sum because the money doesn't have a long time to grow. However, if I'm looking at far down the road, I need a much larger amount invested now to grow to that, right? So it makes sense that the present value gets smaller over time. So now the question is, so those are all the present values. Okay, so now to get the actual present value, I just sum the present values. Present value equals the sum of the above interim present values. Right? And ultimately we get, right, I'm not going to go through the argument with again, but essentially we do the same thing that I did yesterday. Okay, so you would add them up like this. You would multiply by 1 plus R over N. Then you would subtract. You would be able to write down a nice formula in a division, right? And assuming we do that, I'm not going to do it again. I did it here. And you can, if you're interested, you can try to follow that logic and see if you can derive the same formula that I did. But ultimately, I'll just tell you what the answer is going to be. Ultimately, you would get this as your answer. Screen was frozen for a second. Ultimately, you would get this as your answer. You would get the present value is going to be worth R times 1 minus 1 plus R over N to the minus NT over R over N. And again, when we change our notation to use more conventional notation, this means the present value in terms of the payments I want. This was an M, but we change our M to NT. It's 1 minus 1 plus r over n to the minus nt over r over n. And that's the guy we want. What lump sum is needed to get a certain number of payments for a certain time period? Okay, this is what's called the present value of annuities formula. So it's the lump sum needed in order to receive I before E except after C. The lump sum needed in order to receive payments of size PMT over some T years, where we get compound interest n times per year. Okay, so it's called the present value of annuities formula, right? So this is the main star of section 3.4. This is the formula that you need to know. Okay, you do need to know this guy, but he's the less important one, and he's just a rewriting of a formula that we had a long time ago, the compound interest formula. But using that formula, we can derive this formula, which is the main star of this section. So that's the present values of annuities formula. And again, I could solve for this as something else. We can solve for the PMT. And then in that case, we would get the payment is equal to, well, the present value times r over n divided by 1 minus 1 plus r over n to the minus nt. And this is called the amortization formula. Now, I'm going to tell you why that's called the amortization formula. But one thing I do want to note, because this literally even happens to me. So a very common mistake when using this formula, I want you guys to watch out for, is to note. Boop, that negative sign on the power. If you forget it, you're going to be wrong by a lot. You might even get a negative answer, right? Which isn't going to make sense in most contexts. So if you're doing your calculations correctly, you don't want a negative answer because it means you're going to owe money in some form. But sometimes you'll get a negative answer if you forget that negative power. So be very careful. There are a lot of formulas where we type in the powers NT. So your fingers get used to typing that. And then when you need to put that negative there, you just forget because your muscle memory isn't as attuned there. So definitely be careful with that negative power. I'll mention it here again, note. So don't forget the negative power. You will get in trouble. Okay, so that's one thing I would just mention in terms of the mechanics of working through things in class. Why is it called the amortization formula? It's because amort or mort, the root word is actually from mortality, equals death, right? So it's a very morbid reason, actually. So the idea is this formula is often used to figure out PMT needed to quote unquote kill, put to bed, put to death a debt, right? So AKA amort a debt. So there are times when you can use this formula for your own purposes as a consumer. We'll cover examples like that next class. But a lot of the times what you want to realize is that this is the form that's used against you. So oftentimes it's used by lenders against you. So if someone knows, hey, I'm going to lend you a certain amount of money now, I'm giving you a present value now, and I'm going to charge you a certain interest rates, here are the payments you have to pay me on a monthly basis in order to pay off that debt, right? To amort that debt. So it's called the amortization formula, and it's often used in that context most of the time. But you can use it in your own context, especially for things like max purchase price. We won't do an example of that today, but we will next time, and I will leave it in the notes for you to try ahead of time. So yeah, this is the main formula. If you solve for the PMT, you get what's called the amortization formula. And I want to use this formula right away. So let's actually do that. So let's go back to the last question. Okay, is it still in my computer's memory? Yes. Present value of annuity. Right. So back to this question. Okay, which is should be of some interest. What should I deposit now so that I can withdraw $1,000 a month for the next 5 years? Okay, and how much would I save, assuming that the account is making 5% APR compounded monthly? Okay, so here I know the following. I want to receive payments of $1,000. I am assuming that I'm getting a 5% return compounded monthly over the next 5 years. Okay, so under those assumptions, how much do I need now? Right? So what is the present value I need now in order to have this happen? So we know that the present value is going to be PMT 1 minus 1 plus R over N to the minus, don't forget that minus NT. Okay, so that's the relevant formula. So that means I'm going to get $1,000. And assuming that I'm getting 5% interest rate compounded monthly, so that's 12 times per year for the next 5 years. Right, so again, I'm getting 5% compounded monthly. How much would I need? And I did the calculations for you, but again, I highly recommend that you do this on your own. Make sure you're getting the right answer. 52990. Right. So on the test, if you're like, oh, I had the right answer, but I plugged in my calculator wrong, it's not going to work. I am giving you ample opportunity to know how to use your calculator. Okay, so that's what you would actually need. And you can double check me on that. One day I might put the wrong answer here on purpose to see if anyone catches it. Or I'm kidding. I could just make a mistake and put the wrong answer. I'm human, of course. How much do I save? Well, the total payments is going to be what? Well, it's $1,000 per month for 5 years. 5 years is 60 months. So it means the total payments are going to add up to $60,000 over that 5-year period. And I deposit $52,990. And again, remember, you might not have that 53,000 right now or close to 53,000. So the idea is what you would do is you'd first set up a sinking fund to save up to that much. But you know that once you hit that mark, you can stop saving because you'll have enough. So this means I save. At this point, it looks like 7,000. So this might be worth it, right? It saves you 7 months of payments. You can get the money you want for almost a year less, well, almost a little more than half a year less work. So that might be worth it. And again, 5 years isn't really a long time. So that's 7,000, still in the grand scheme of things, not a huge sum of money, but might be worth it, depending on your situation. So that's the last example, but I want to leave you with a couple examples to try for Friday. I believe I typed them out. They should be here, here somewhere, right? So this is some examples to get you to use the amortization version of this formula. So I have one of the examples that shows you how this formula can be used against you, like say by someone lending you money, and how you can use it for you in your own value. Something is going on. Anyway. Okay, I should have enough. My battery wasn't plugged in. Okay, so for example, let's say you want to go into business, you need $100,000 capital, so you don't have $100,000, so you go to borrow $100,000. So you go to these people and say, hey, lend me $100,000. They say to you, all right, I'll lend you $100,000. However, I'll charge you 3.99 APR compounded monthly. And here's how much you're going to pay me. If you want to double check their math, how do you figure out what your payments need to be to amort $100,000 debt at that interest APR, right? What are your payments going to be, right? That's why it's called amortization. So this form is often used against you to calculate your monthly payment. So if you go out for a mortgage or a car loan or something like that, and they tell you, oh, if you want to borrow this much money, this is what it's going to cost you per month. This is the formula that they're using. So that's how it can be used against you, and you want to calculate your payments. You can use it as a consumer to figure out something like the max purchase price. So say you want to get a car and you budgeted and you know that, oh, I can afford $450 a month on a car payment, right? So let's say you go to a dealership, they say, all right, we offer 5-year car loans at 2.99% APR compounded monthly, which probably is a red flag because car loans are usually simple interest. So if anyone tells you that, probably run for the hills. However, the benefits here is like no credit check, just have a job and you drive. So maybe they're offering steep interest rates because they don't require a lot of capital on your part. If you want to take advantage of the deal, what car price should you negotiate for? Can you afford a $50,000 car? Would it be a $30,000 car, $15,000 car? Like what price should you negotiate for? What kind of car should you be looking for, right? So that's how you as a consumer, you can know before you go out shopping, if you know what you can afford per month and you know you're going to need to borrow some money at interest, what is the max price you can go to? This is called the max purchase price application. So we'll do these 2 examples next time, and that will actually finish up 3.4, and then we'll start linear programming. So by the way, just a reminder, when we do linear programming, I'm going to show you how to solve the problems on a computer, on Excel, on Python. So make sure you have your Excel game and your Python game up to scratch. You have the stuff installed on your computer. You know how to use them to some basic degree because we're going to use those next week. Also, because 3.4 is finishing next week, that's the last section in chapter 3. It means you can do all your chapter 3 homework this weekend. And I would do it this weekend, even though technically it's not due till mid-March. You don't want to put off everything till the last minute. So by this weekend, try to get through all your chapter 3 homework to make sure you're getting everything. And at that point, you'll know that if you don't get something, you can ask me. You can go to office hours. You can go to tutoring. You can get ahead of it right? So that is what I would say. Any questions before we go? But that's all I have for today. I'll leave these examples in the notes so you can do them. But any questions? No? Okay. We will stop there. Have a good rest of your day. I will see you guys on Friday. So see you in the next one. Ciao.